All right, so let's now give a definition of what it means by being a dot product. So dot product here is intended to be a multiplication method for two vectors. So now let's start out with that definition first. I'm going to say let a vector u and a vector v be vectors in R2. So remind yourself R2 here simply means, and we are just beginning with our understanding here, but I kind of vaguely use that concept of R2 here as being a two-dimensional space. And then as we progress through the quarter over here, you will have a much better understanding of what a space is. So right now, keep it at just the two-dimensional space as you usually understanding it. So the dot product between u and v, the two vectors u and v here, we're going to take the symbol u dot v and make sure you use that dot symbol here unusually bigger than the usual dots for multiplication. So the dot product now is defined to be u1 times v1 plus u2 times v2. So u1 and u2 in my formula, they are, remember, since we're looking at vector u and v are being vectors in R2, then u1 and u2 are the two components of your vector u. And so vector u is supposed to look as a column vector this way, where u1 is the component 1 and u2 is component 2. And v1, v2 in this definition is simply the two components of your vector v right here. So vector v is written as v1 and v2 right here. And so back to this definition, we define the dot product between the two vectors in R2 as being the component-wise products between component 1 and component 2 added together. All right, and then so what about when we're in R3, or in other words, the three-dimensional real space? Then vectors in real space got three components. So let's say we're going to have a vector u being with components conventionally u1, u2, and u3. And then in linear algebra, you guys, everybody has already been start getting comfortable with the idea of writing a vector as a column vector. And your vector v in R3 is written as a vector v1, v2, v3. And so that concept we've learned about, that definition we've learned about how to take the dot product between two vectors in R2 can actually be extended to R3. So because R2 and R3 is simply just a matter of each vector here has an extra component. So why not define? So here be in R3. So that's what those two vectors u1 and u and v are. And so in R3, similarly, the dot product between two vectors u and v are simply being done by u1 times v1 plus u2 times v2 plus u3 times v3. And there we go. We have another definition for how we can take the dot product between two vectors in R3. So now let's do a couple examples. Okay, so in this example, let's say we just simply want to calculate the dot product between some two vectors u and v. So how about I'm going to produce part A of this example right here, where I'm going to say I'm going to be having given vector u here being 2, 1, and a vector v being 3, -2. And so immediately, as we have seen now the definition of the two vectors, each one of these vectors now clearly are being in, each one of these vectors is clearly being in R2. So these are, we are now working in R2. The dot product between U and V in this case right here is simply just components of U, component 1 of U is a 2, times component 1 of V is 3, plus component 1 of U is 1, times component 2 of U is 1, times component 2 of V is -2. And so this answer here, after doing the quick calculation right here, that's 6, and that's -2. So we're looking at the final answer here is being 4. So notice the final answer we've had here is not a vector. It's actually a scalar. Notice that what we have here is a scalar. But that's our answer. In the same example, let's look at how we can find the dot product of vector U being 1, 1, 3, and vector V being 3, -1, 4. So now in this part B of the example, then obviously our vectors are in R3. And so in that way, but similarly, it's not really going to change the way how we find the dot product. So U dot V is simply first component of U times first component of V. It's defined to multiply that way. So 1 times 3 plus, so now second components of U times second components of V, 1 times -1. And then now third component of U times third component of V, 3 times 4. So now we're looking at 3 minus 1 plus 12, and that's giving us a final answer again being 14. Notice again that this final answer of a dot product is being a scalar again. Even though we switch over to working with vectors in R3, the answer is the same kind. It's a scalar. And so in that reason, so after looking at the result from the two parts of that example, that first example being brought up right there, then you can see that this is the reason why a lot of times dot products is sometimes the same as a scalar product. Sometimes people refer to dot product as a scalar product of two vectors. And so now space outside of R3 and R2, there are higher dimensions. And so generally, now we're going to extend that definition of dot product for vector in Rn. So in Rn, generally the two vectors are going to look like this. They're going to have components u1, u2, up to un. Each vector in Rn has n components. And then the vector v here is going to have components v1, v2, so on and so on, to vn. And so we are going to extend that definition of a dot product into vectors in Rn. And so now in Rn, vector u dot vector v is going to be the same as u1 v1 plus u2 v2 plus u3 v3 all the pairs of components multiplied together, and add it all until we hit to the end of the two vectors product. So un times vn. And this is the definition for a dot product of two vectors in Rn. And so as to now, as we keep getting more fluent and more fluent with this concept of taking the dot product of two vectors, then you can see that the core idea of taking a dot product is it's producing a sum of all those pairwise of products between u1, v1, u2, v2, and so on up to vn. And so be prepared with the idea that sometimes you might have seen in some different places over the web or in some other textbooks, dot product can sometimes be used in a convenient summation notation. Even though I am not too particular about you must be able to use summation notation, but it could be convenient sometimes. But the definition here can have a different representation, that u dot v equals to the summation of all pairwise products ui times vi. So each of these v with the index i's right here, or came out from the different components corresponding different components, but these are scalars. And then we're taking the sum for I from the first component to the nth component. So that's just something worth your attention to know. So at this point, let's look at some more detailed understanding about length of vectors. So let's say you're in R2. A vectors can be regarded as some vector like this. It could be simply a vector that points out from the origin out to a point xy. Or I should have used, this is x1 components and x2. So this point right here is x1, x2. But geometrically, x1 is this length. That's x1. x2 is this length. And so the geometric meaning, the geometric length of this vector, let's say we're going to call this vector the x vector. And so the x vector here is simply the length of that vector. You have seen in some of your past courses that the length has a symbol double vertical line like this. So length of a vector x bar here, Pythagorean theorem explains quickly that it should be just the square of one height of the square of one leg plus the square of the other leg. So here it's simply just x1 square as this component here, being the rectangular leg right here, square, plus x2 square. And so that's consequently ended up with vectors in R2. Let's say a vector x right here in R2 has a length being x1 square plus x2 square. Then we take the square root. That's how we find length. Or alternatively, you might see another common form of saying writing length, expressing length is that the square of that length is equals to x1 square plus x2 square. Some textbook authors is more comfortable expressing length this way, even though it's in the form of a length square. And then some of you might have seen in some of your Calculus 3 courses that in R3, the length for a vector in R3 again is the components 1 square plus the square of component 2 plus the square of component 3, and we take the square root again. And then alternatively, some authors again decided to write the length square of a vector is to be in R3 is to be the sums of all the squares of components. So x1 square plus x2 square plus x3 square. These are the two different forms of how we can express different ways to find lengths of vector in R2 or vector in R3. So here, in linear algebra here, even if you're in a space that's much higher dimension, let's say again Rn, then we can generalize the idea that the length of a vector x in Rn space is going to be just simply the square root, and inside of that square root it's x1 representing components 1 of your x vector x square plus x2 square plus x3 square, and keep adding, etc., etc., until we hit to the n of your vector n, the last component. Or some other textbooks also write that as the length square is to equals to x1 square plus x2 square plus x3 square plus xn square. So that's just a brief look at some of our understanding in terms of how we obtain length. And then just now we learned about the dot product. So dot product, when we take a vector u in, let's say for now u is in R2, this symbol of mine means being in or an element of. So anyway, so let's say our vector u is in R2 for simplicity. U should have components u1, u2. What if we take the dot product of our vector u with itself? Then so the dot product of u dot u, the dot product method, or the definition, according to the definition of the dot product, it says we're going to go u1 times u1 plus u2 times u2. And that turns out equals u1 square plus u2 square. And so at this point, all of a sudden, blending our new understanding about the dot product between two vectors, we just, wait a minute, we found out something, isn't this? And that was the reason why I keep mentioning about some others of other textbooks keep writing a length as a length square, because the u1 square plus the u2 square right here turns out indeed this is the length of your vector u square. Or as a matter of fact, what we now just recognize, we discover that any vector u dot itself is going to equals the length of that vector u itself being square. And so algebraically, at this point, we understand that we arrive at the length of the vector is simply the square root of the dot product. And so here in this class, we are going to define how to find length. So length in our class here, entirely based on the dot product, then we're going to define the length, let u be a vector. Then the length of the vector u is simply defined to be the square root of the dot product u with itself. And so I gave my explanation based for simplicity. I use my vectors in R2. However, this definition should be true for vectors in Rn. It could be R2, it could be R3, it could be Rn, R4, R5. All right, so let's look at another example. Let's say I'm going to be, for simplicity, be using a vector in, how about vector u? Being that vector we've used in the earlier example, 2, 1. So let's find the length of u. So the notation here, the symbol here is indicating that this is an indication that we want the length of the vector u. But the length, now at this point, we have an understanding that the length is, by definition, we dot u by itself, and we take the square root. So before we start too far right here, you can see that I purposely wrote that work here so that it carried out as the order of operation here, but you definitely need to take the dot product between u and itself first, and then we take a square root of that. And so in this way right here, the dot product of u and u is going to be 2 square in parentheses plus 1 square, and we take a square root. So 2 square give me 4 and 1 square give me 1. So here we're looking at square root of 5. So now I'm saying that the length of this vector u is square root of 5. Okay, so we found in the example we just finished that for the vector with components 2, 1 in R2, then we can understand that as a vector like this, pointing from the origin out to that coordinates point 2, 1. And so this vector has length, to remind everybody again, the length of this vector is square root of 5. So the idea now is that for vectors, vector has directions. That's what the coordinates are responsible for, where the vectors are pointing. And what we just now calculated in our example was the length. So the same direction, but it could happen that sometimes some vectors is longer, and same direction, but some vector is shorter. So the idea we're looking at now is that there are the needs for looking for those vectors where it could be pointing in the same direction with this vector u 2, 1 or 2, 1, but we strictly desire for only length 1. And so that brings us into the concept of a unit vector. As the most fundamental understanding, we need a unit vector to be, a requirement here is a unit vector must have a length. Length 1. It's a need, it's a desire that sometimes it comes straight to us, and so we give a fundamental definition that a unit vector is just any vector pointing in any direction, but we need that it must have length 1. And so now, in our a little more mature understanding that we blend the concept of dot product into it, then now we have at our level here learning linear algebra, then we're going to redefine unit vector in terms of a dot product. So a unit vector is a vector having the dot product with itself equals 1. Okay, and so why would we define a unit vector this way? Think about it again. Back into the fundamental definition, what we really are looking for in a unit vector is that a unit vector must have length 1. And didn't we just define that length of a vector u is simply just the square root of u dot itself? And so length 1, if what we want here, the length of the vector u being 1, if that's what we desire, then algebraically the length of u squared also equals 1. And once again, this length of u squared right here is that consequently lead to that notion of u dot u, because u dot u is exactly length square equals 1. And so for convenience, we use this new developed way to define what it means by being a unit vector. So a unit vector, once again, is a vector that's having u, is a vector u dotting itself, right? Yes, I should have redefined my definition a little bit, but a unit vector is a vector u having that property u dot u equals 1. So, in another example, let's verify that a vector defined as 1 over square root 2 and 1 over square root 2. So we're going to have a vector with two components, 1 over square root 2 and 1 over square root 2 again. Let's verify that this vector is a unit vector. And so, straight out from the definition we've learned earlier, then all we need is to find out whether or not u dot u, let's find out what that equals to. So the vector u dot itself is going to be 1 over square root 2 times 1 over square root 2 square plus 1 over square root 2 square. And that gives me 1/2 plus 1/2. And that is equals to 1. And so now we're making our conclusion that we have just now verified. So the vector u equals 1 over square root 2 with the other components 1 over square root 2 is a unit vector. All right, and then let's look again at the idea about the scalar, how multiplying a vector to a scalar will affect a vector. Now say, let's start out having a vector in R2 right here, and here's our vector pointing into some direction. And so we've seen in earlier reading that if we multiply this vector here with a scalar, then sometimes multiplying to a scalar, it will lengthen the vector into something that's longer. And that's the whole reason why we call those numbers that we multiply to a vector, we call those numbers scalars, because they can scale your vectors either longer or shorter. And so sometimes multiplying, so here multiplying c to v, we might end up with getting a longer vector. I'm talking about going from here all the way to there. Or sometimes we can multiply to a scalar that make v shorter. Another scalar can also make v become shorter, but these are all pointing in the same direction. And so we also agreed earlier that length of any vector is the square root of v dot v. But the dot product is a scalar. So consequently, square root of a dot product is a scalar. And of course, length now is a scalar. So I just need to emphasize this before I take that into the next concept. So length of v of any vector v is a scalar. Is a scalar. And so consequently, 1 over v is also a scalar. And why do I keep beating around the bush with all these scalars pointing out for you what a scalar is? And I mean, what quantity can be regarded as a scalar? Because now, as long as you have a scalar, then you have your right to multiply a scalar to any vector. And so now, starting with a vector v, we already found out that 1 over the length of v is a scalar. So what if we multiply that length of v, that sort of scalar, to v itself? Then doing this actually gonna make the vector shorter. And let's call this some new vector. Of course, it's not the same vector as v anymore. It's shorter. But we're going to call that as a vector u. Okay. So here's what's special about this vector u right here. U is the unit vector. In the same direction. As v. And so as we multiply a scalar 1 over length of v to a vector v itself, we definitely produce a new vector. However, that new vector has a close relationship with v. It is the unit vector that's pointing in the same direction as v. All right, so now let's find out how useful that what we've just learned there is going to carry into this example over here. But I'm going to have a vector v is to be 3, -2. And everybody can quickly double check for me that this vector is not a unit vector itself. It's going to have some length higher than 1. But what I'm looking for now is that in this example, we want to find the special unit vector in the same direction as v. So that's the instruction of the problem. We want to find the unit vector it's a unit vector length 1 but point in the same direction as v. And so here's how we performing this task right here. What we need to do is simply, first we're going to produce a scalar 1 over the length of v. So that's the first step. We're going to simply just produce a scalar 1 over the length of v. So that is simply 1 over, so now the dot product kick in, and the definition we've learned earlier is going to say we're going to take the dot product of v itself. So just to remind yourself again that v is 3, negative 2. And so the length of v in the denominator here is going to be 3 square plus negative 2 square, all of that in square root and in the denominator. And so what we are looking at here is going to be a scalar 1 over square root of, let's say that's 13. 9 plus 4 is 13. So now this scalar, what I'm going to do to it, I am going to multiply this scalar 1 over square root 13 to the vector 3, negative 2, which was our vector v. And so doing this, of course, it's not the same vector as v anymore. So that's why I'm calling that it's a vector u. But this vector here, and by the way, let's go ahead and do the scalar multiplication. It's going to consequently end up for us a vector 3 square root 13 and then negative 2 square root 13. Okay, but now, ladies and gentlemen, now I'm telling you that this new vector right here, this vector u, has length 1. It points in the same direction with v, and it has length 1. So let's quickly check right here. Let's check this vector u right here, and of course the reason I can guarantee you that u point in the same direction of v because u is simply just a scalar multiple of v, so that's in the same direction. But now I'm mainly gonna check to see whether or not our calculation here gave us a final vector u that's being in length 1. And so all you have to do, u dot u. And as long as our final answer for u dot u here with our currently found u, if that currently found u turns out being 1, we were successful. And so 3 over square root 13, that's the first component, but u dot u by itself. And so now at this point, let's get straight into it. 3 over square root 13 square, that's the first component, plus, so now I'm going to look at the other components, negative 2 over square root 13 square. The good thing with square in this problem is that they're going to cancel out those square roots. And so we're looking at I apologize. We're looking at 9 over 13 plus 4 over 13. And that gives us 13 over 13, which is 1. So we did get what we want. What we wanted here was to find a vector u pointing in the same direction with v, and doing it this way, what did we do? We take that vector 1 divided by the length of v right there, multiply that as a scalar to the vector v, and here consequently we ended up with that. And we checked that that vector, that new vector, is a unit vector, length 1.